we want to take a look at really the Hamiltonian. I've done a lot of Lagrangian stuff. I've done a lot of Newtonian stuff. And I think the best way to think about and really get a feel for Hamiltonian mechanics is to do a problem 3 different ways. And I've done this before, but I'm going to do it again. In this case, I'm going to do it with the pendulum. So I'm going to take a pendulum. So it's a mass on the end of a string of length r. You can't call it L because there's a Lagrangian. And it starts off with some angle theta like that and swinging back and forth. Yay. We've done this a bunch of times. And so I'm going to do this. I'm going to solve this with Newtonian mechanics, and then I'm going to solve it with Lagrangian mechanics, and then Hamiltonian mechanics. Let's get started with Newtonian. So in Newtonian mechanics, what we do is we really want to use this. We want to say F net, that's a vector, I can't spell, equals, let's say, ma, right? The net force is mass times acceleration. That's what we want to do. So if I do that, I need to know what forces there are. So in this case, I have 2 forces. I have the gravitational force mg. I have the tension pulling in the direction of the string t. And those are the only 2 forces I have on this pendulum. And so I could say, oh, that's pretty easy, right? T plus mg, they're vectors, so I'm adding them, is ma. And then can I just solve for a? And no, I can't. It's not that easy. Because although I can get an expression for the gravitational force, mg, the tension is not something that I can calculate. Well, I can, but I have to use some tricks. So it's not just, there's the tension equation. There is no such thing. And in fact, this is a force of constraint. This means it does whatever it needs to do to keep the distance from here to there as r a constant, which is a constant. Now there's a couple of different ways you can deal with this, but this is classical mechanics. We're like in mature physics. So we're going to do it the mature way. And we can do this. But since I have this mass constrained to move in a circle so theta can change, but this distance can't change, maybe it would be best to use polar coordinates. So let's use polar coordinates. So in that case, let me just redraw it really quick. And I'm gonna have a little bit different polar coordinates here. I'm gonna have this is my r value, and that's my theta value, so it's down. That way it matches right there. And then I can still write Newton's second law, F net equals net. I'm having trouble with that. Ma. But in polar coordinates, then I have the polar unit vectors. I have r hat, which would be this way, and theta hat, which is that way. And r hat and theta hat are not constant with time, and so that does make things a little bit difficult. Because if I say the vector r is r hat, then if I take the derivative of that, I have to take the derivative of r, which you get r dot, and r hat. And I'm not going to derive this. I've already have a video of this, and it's pretty awesome. And if I forget to link to this video down below, then yell at me in the comments down below. But I will post that video. But in the end, in polar coordinates, the acceleration vector is r double dot minus r theta dot, r hat, plus 2r dot theta dot plus r theta double dot theta hat. So just a reminder that if I write r dot, that is the derivative of r with respect to time. R double dot, we like to use this double dot notation, is the second derivative of r with respect to time. It's because there's 2 dots. Okay, but now I have the r component of the acceleration and the theta component of the acceleration. And this is really nice in a pendulum like this, because if r equals r, and you can hear how I pronounce that, right? R equals r, that's capital R, and that's the variable r. But if that's the case, then r dot is equal to 0, r double dot is equal to 0. I take the derivative of a constant, I get 0. So that makes it a little bit easier. Now I don't really care about, I can write down the forces in the Newton's second law in the r direction. I guess we should do that. F net r is going to be equal to 0. And now what forces are acting in the r direction? I'll draw them up here. I have the tension in the negative r direction. negative t. And then I have this component of the gravitational force. It'd be plus mg cosine theta. So that's an equation, but I don't really get an equation of motion from that because it's not very useful. If I look at the theta hat direction, F net theta, that would be equal to, well, what forces are acting in the theta direction? It's just a component of this, right? So if that's mg, then this is going to be mg sine theta. And it's in the negative theta direction. Increasing theta is that way. So I have negative mg sine theta. And that is going to be equal to, see, this is why, whoops, that's not true. F net r is not 0. It's, you should have stopped me. It's your fault. It's equal to r double dot 0, but I still have this negative r theta dot. So actually, I could use that. Yeah, okay, but that's fine. We're going to use this equation over here. So the O times m. You make one mistake, and it just throws you off, right? And then you're like, should I start over the video? No. Never start over the video. Just keep going along. Okay, so we're over here. This is my theta hat, my theta direction component. I have r dot, which is 0, so that term goes away. So this is going to be equal to r theta double dot. So let's solve times m, because that's mass times acceleration. This is the force, mass times acceleration. Of course, the mass cancels. I can solve this for theta double dot, and I get negative g over r sine theta. So now I have a differential equation that I would need to solve in order to find the equation of motion. So let's go ahead and do that. In the first physics, you would say, well, if theta is small, then sine of theta is approximately equal to theta. And then you can turn this into a simple harmonic oscillator. But we're not going to do that. We're going to solve the real version. So here's the differential equation that we have. Theta double dot is negative g over r sine theta. And if I break this motion into tiny steps, delta t of, let's say, 0.01 seconds, then I can assume theta double dot is constant over that time interval. And if theta double dot is constant, I can write theta double dot is the change in theta dot with respect to time. And I can write that as theta 2 dot minus theta 1 dot over delta t. So theta 1 dot is the theta dot value at the beginning of the time interval. Theta 2 dot is at the end. So I can solve this for theta 2 dot. I get theta 2 dot is equal to theta 1 dot plus theta double dot delta t. Kind of a big deal. Now let's assume, which seems kind of dumb because I just changed it, let's assume that theta 2 dot is constant, which is obviously not. I just changed it. Okay, but if that's the case, I can say theta 2 dot is equal to delta theta with respect to time. And so that looks like theta 2 minus theta 1 over delta t, and I get theta 2 is theta 1 plus theta 2 dot delta t. And I put the 2 here and not the 2 up there because you want to do this calculation before you do that one. If you do it out of order, then your error is large. Okay. So I'm done with that one time step, right? So I calculate theta double dot. I use that to update theta dot. I use that to update theta, and then I just do it again for the next time interval over and over and over again. But I need numbers, right? So I need to know the initial theta. I need to know the initial theta dot, and I need to know, g over r. Okay. So I put some numbers right there. So let's use these numbers and make this happen in Python, and then we'll do Lagrangian mechanics. So I'm switching over to Python, and if you've watching my videos, you know I've done this like 8 billion times, maybe. Maybe not, but you get the idea. Okay, so blank trinket. I'm using Web VPython because I like it, and because the graphing is really nice, and it's free, and Okay, so let's just make a graph. I'm gonna plot theta versus time. That's what I'm gonna plot. So graph is G1. G1 equals graph. And if you have questions about graphing in Python, let me know in the comments down below. I have tons of stuff about graphing in Python, and I'll post a link to your comment, because that's what I like to do. I like to help out people. So the graph, I'm going to give it an x title. X title equals time. I won't put the units. Y title equals theta. And then I'm going to give it a width of 500, height of 2. This is the pixel size. And then I'm going to have a graph to plot. F1 equals G curve. And I like the color blue. I don't know, it just shows up nice. Color.blue. Now I need all my variables. G, M. I said that even that doesn't even come in there. What did I say it was? 0.1. Theta, this is my initial theta. At 45, it's going to be 45 times pi divided by 180. I need to convert that to radians. This version of Python prefers radians. There's a way you can do it in degrees, but I always convert. Okay. I need my initial theta dot too. So I'm going to say theta dot equals 0. Now I need R. I never said what R was. Ooh, that was bad. It's a string this long. So I'm going to say 0.4 meters. Is that big enough? Okay, now I need t equals 0, dt equals 0.01, and let's run this for 5 seconds while t is less than 5. Let's put this. I like dots too. Dot equals true. Let's just put the marker on the end on the graph as it makes it. So while t is less than 5, rate 100. That says don't do more than 100 calculations per second. So this will run in real time. And the number one thing, calculate theta double dot. Theta d dot, that's why I'm calling it. You call it whatever you want. You could call it alpha because that's the angular acceleration. You be you. It's your program. I'm doing it this way. So it's negative g times sine of theta divided by r. Negative g over r sine theta. Now I'm going to update theta dot. I already have a value of theta dot. It's 0. And I need that to change it. So I'm going to say theta dot equals theta dot plus theta double dot times dt. And if this is your first time in Python, welcome to Python. I hope you're having fun. This is not an equation. This is a make equal to equation. This is an assign, right? So we don't have to put 1 theta dot 1 theta dot 2. We're just changing the value of theta dot. Now we can do the same thing for theta. Theta equals theta plus theta dot times dt. And now I need to update time. T equals t plus dt. And now I need to plot the thing. F1 dot plot t theta. Let's run. I didn't even save it. That's because I'm just like a crazy person. I'm not even going to save it. I'm just going to run it. And it worked. Okay, so if you want, we can check this. We can't check this for this value, but if you put a small angle for theta, then you should get a cosine function. You can check the period of oscillation. You can do all that stuff. If you mouse over this graph, it'll give you the times, so that's good. So, but it looks like it's working, so now I can save it. So let's call this Newtonian pendulum example. I don't know what I'm calling it. Did I even spell pendulum right? I don't know. Okay. So that's Newtonian mechanics. Done. Do it again. We're going to go back to the paper and do Lagrangian mechanics. Okay. So Lagrangian mechanics works the following way. It says that it first, and I'm going to give you the crash course version of this. Is crash course trademarked? I don't know. So if we define the Lagrange, okay, number one, let's just call this Lagrangian. So what we do in Lagrangian is to pick a variable, a generalized coordinate, and it can be anything to describe the situation. And so in this case, we could pick the angle theta. That seems like the obvious choice. So I can describe the system with just one coordinate theta. I don't have to use Cartesian coordinates or polar coordinates or any real coordinates. I can just pick a coordinate. If I do that, I can use that coordinate to determine the the Lagrangian, which is T minus U. So T is the kinetic energy. In terms of that coordinate, and U is the potential energy. And if I do that, if I create my Lagrangian that way, then I have the following is true. And this basically what it says is that if we integrate over all possible space-time curves, the space-time curve, not space-time, but the action curve, it's called an action curve, the one that minimizes, the equation that minimizes the path integral of the action is the equation of motion. I messed that up. But the important thing is that the partial of L, if you have any variable, we'll use theta, with respect to theta, minus the derivative with respect to time of the partial of L with respect to theta dot has to be equal to 0. And so you can do this for more than one coordinate. You just do it for each coordinate, and it works really well. The Lagrangian works well in cases where, 1, the energy is conserved, and 2, you have some type of constraint, right? So here I have a constraint where it has to stay along this path, and so I can make up new coordinates. So Lagrangian works really great with constrained situations, where Newtonian mechanics doesn't really work that well with constrained equations. Okay, let's do it. So let's write the kinetic energy. I don't know, so this is a mass m, and that's distance r, and that's the angle theta. I actually don't know the kinetic energy for this, and we could say, oh, it's polar coordinates, we know what it is. And I'm going to give you the very fast version of this. If I don't know how to write kinetic energy, which I don't, right, then I write it in terms of Cartesian coordinates. So in Cartesian coordinates, I know this is true. The kinetic energy is 1/2 m x dot squared plus y dot squared. That's the kinetic energy in Cartesian coordinates. We always know that. So now if I get x and y in terms of theta, then I can take the derivatives and I can start making stuff happen. So this is my origin right here. That's my x origin. So I can say x is going to be equal to r, that sine theta. In this case, y is negative r cosine theta. Is that cool? Right, because it's down below there. So that's my y value is negative r sine theta. So I know that relationship. Now I can take the derivatives with respect to time of x and y. X dot is going to be equal to r theta dot cosine theta, right? Because I take the derivative of sine theta and I get cosine theta, and then I take the derivative of theta and I get theta dot. You got to take the derivative of theta dot also. And then y dot is going to be equal to r theta dot sine theta. So here I took the derivative of cosine theta and I get negative sine theta, but I already had a negative, and then the derivative of the theta dot. Now I need to square both of these and add them. So I get x dot squared plus y dot squared. I did that wrong. Wow, that's a double mistake. No, that's right. That was right. I don't know. Again, mind blank. Let's put OK. Let's see. So, yeah, I was thinking there was two terms. This is pretty easy then. So I get r squared theta dot squared cosine squared theta plus r squared theta dot squared sine squared theta. And then I can factor out the r squared theta dot squared, and I get cosine squared plus sine squared is 1. So it's just going to be r squared theta dot squared, which you kind of already knew that. So I know now t is 1/2 m r squared theta dot squared. Like that. Now what about the potential? Again, I can use, I know u is mgy. So I just put in my value for y, and I get u equals negative mgr cosine theta. Now I can write the Lagrangian. T minus u is 1/2 m r squared theta dot squared plus mgr cosine theta. So it's plus in this case because I had the potential's negative and then the Lagrangian's negative minus u. There I have the Lagrangian. And you may think, this is a lot of work just for a stupid pendulum. But remember, there was a lot of work for Newtonian mechanics too. I mean, I skipped all that stuff about finding the acceleration vector in polar coordinates. So, okay, so this is my Lagrangian. Let's write that down. L is 1/2 m r squared theta dot squared plus mg r cosine theta. So now I can do the Euler-Lagrange equation, which says the partial of L with respect to theta minus the time derivative of the partial of L with respect to theta dot is equal to 0. So let's do this in parts. Let's do this part first. The partial of L with respect to theta is equal to, okay, this is a partial derivative. There's no theta here, so I don't have anything. I have a theta there, so the partial of cosine theta with respect to theta is minus sine theta. So I get minus mg r sine theta. There's no theta dot because I'm taking a partial with respect to theta. Now let's do this. The partial of L with respect to theta dot. Well, there's only one theta dot. It's right there. And I can use the power rule, right? So I bring the 2 down. I get 2 over 2. And then I get m r squared theta dot. Now I can take the derivative of this, the derivative with respect to time of the partial of L with respect to theta dot is m r squared theta double dot. That's the only thing that changes with time. And if this minus that is equal to 0, then this has to be equal to that. So I get m r squared theta double dot equals negative mg r sine theta. And then if I divide both sides by mr squared, I get theta double dot negative g over r sine theta. So you'll see that we get right back to the same differential equation we had for Newtonian mechanics, and that may seem like, not a big deal, but that's what it is. So it's really a different way to get that differential equation. With Hamiltonian mechanics, we're actually going to get a slightly different differential equation. You could get to this, but we're not going to. Okay, so let me write down my Lagrangian because we need that for Hamiltonian. 1/2 m r squared theta dot squared plus mg r cosine theta. Okay, so now we're going to do Hamiltonian mechanics. It's I remember the first time I did this, it's like, what is the point? If you're going to find the Lagrangian anyway, then why are you doing Hamiltonian? And we'll talk about that in the end. So the Hamiltonian is defined for a number of systems in terms of the momentum and in terms of the coordinate. And you can have more than one coordinate, of course, but we only have one coordinate here. So in general, first of all, we define momentum, which you could say, oh, momentum is mass times velocity. That is sometimes true, but if you have strange coordinates, you have strange momentums. And so it's not always obvious. So in general, the momentum P is defined as the partial of L with respect to theta dot. And for my case, it could be Q dot, right? If you want to do a generalized version. And then I can write the Hamiltonian H as P theta dot minus L. So again, we're using the Lagrangian, and so you got to write the Lagrangian either way. But there is a difference at the end, and I will show that to you. Once you do that, then I get two. See, there's two Hamiltonian equations. I get theta dot is equal to the partial of H with respect to P, and P dot is equal, which is kind of fun to say, P dot is negative the partial of H with respect to theta. And again, if you have multiple variables, this would be Qi, Pi, Pi dot Qi. So, but we only have one variable here. So that's the Hamiltonian. Let's go ahead and do it. Number one, I need to find the momentum. So let's find the momentum. P is equal to the partial of L with respect to theta. There's my L. So if I take the partial of this with respect to theta, there's no theta term right there. There's a theta dot. But there is a theta term. Oh, no, I'm sorry. Ha. If you're counting errors, you're like, oh, he made another mistake. Yeah. It's okay. We make mistakes. So the partial of L with respect to theta dot, that's the only theta dot in there. So I take the partial and I bring down the 2, and I get m r squared theta dot. So that's my momentum. Now I can write the Hamiltonian, right? Because I have momentum, I have theta dot, and I have L. So H is going to be P theta dot. So that's going to be M r squared theta dot times theta dot squared. And then minus L, I get minus 1/2 M r squared theta dot squared. And then I get minus mgr cosine theta. Here I have an mr squared theta dot squared minus 1/2 of that, so this just becomes 1/2. So I get h equals 1/2 mr squared theta dot squared minus mgr cosine theta. That's my Hamiltonian. And you'll notice that it's the same as the Lagrangian. It ends up in this case being the same as the Lagrangian, except there's that plus as a minus sign. This actually is the kinetic energy plus the potential energy, because the potential energy was negative. So this is the total energy. Total energy. Now, it doesn't always have to be that way. Okay, just be careful. We think of Hamiltonian as the energy, and usually you're going to have it that way, but it doesn't have to be. Okay. Well, we got the Hamiltonian. Let's do the first Hamiltonian equation, the partial of h with respect to p. Okay, well, I can't do that because I have theta and theta dots. So I need to go back over here and get h in terms of p. So this I want to get. What do I want to do? There's a little trick here, right? I want to get theta dot squared. So I'm going to square this side and square that side. So I get m squared r to the fourth theta dot squared equals p squared. And then if I divide, you can see if I divide p squared by 2mr squared, so if I get p squared over 2mr squared, then I get 1/2 mr squared theta dot squared. So it does work. So this, we're going to write, instead of theta dot, we need to convert theta dots into p's. So I guess I need to rewrite my Hamiltonian, and now I'm running. I feel crunched for room, so let's write down the Hamiltonian. H is p squared over 2m. Was that right? 2mr squared. Yeah. What? I got that right? P squared, I'm looking at my notes. I didn't write it down. Okay, let's just double check. So, p squared divided by, that is 2mr squared, is that, right? So, p squared is this, divided by 2mr, yeah. Got it, okay. Minus mgr cosine theta, and then my two Hamiltonian equations were theta dot partial of h with respect to p, and p dot is negative the partial of h with respect to theta. Where's it theta dot? That's right. Okay, so partial of h with respect to p. So if I take the partial of this with respect to p, the 2 comes down front, and I get p over m r squared. That's it. And that is going to be equal to theta dot. Now let's take the partial, negative the partial of h with respect to theta, and if there's no theta there, over here I get negative mg r sine theta, right? I already had a negative sign. I take the partial and that goes away, but then there's a negative sign right there, and that's going to be equal to p dot. Just double checking my notes because sometimes I make mistakes. Theta dot, got it. Okay. So we're done, because if you wanted to, you could take the second derivative of this and you get a p dot, and you can plug in this and you get back to the same equation. The same theta double dot is negative g over r sine theta. Okay, you can get back to that. And I'm really messy because I'm just excited about the next part. But you don't have to. Because I actually can solve this equation using two first-order differential equations. So what we're going to do is start off with theta equals something. Let's say 45 degrees. P equals 0. The same thing I had before, right? And then I can break it into time steps. Delta t is 0.01. And I can assume theta dot's constant. So I can say theta, let me do the p first. P2 is P1 plus P dot delta t, right? That comes straight from P dot is delta P over delta t. Theta dot is delta theta over delta t. So if I know the starting momentum, I can calculate P dot right there. I can plug it in here and find the new P. And then I can do the same thing for theta dot. I can say theta 2 is theta 1 plus theta dot delta t, and I can calculate theta dot right there. So what I'm going to do, calculate P dot, update P. And then I just updated P, so you actually want to do it in this order. I'll show you it doesn't work very well. And then you want to update theta, because P is a higher derivative term. You want to do the higher order things first. So you do that, update P, and then update theta, calculate theta dot, and update theta. And so I have two first order differential equations. And again, we need to model that numerically in Python. So let's just jump back over to Python and see if we get the same thing. And then I'll show you a phase space plot because that's kind of cool. Okay. I called this Hamiltonian pendulum already. No, I didn't. I'm down here. So let's just copy everything. I guess I could make a copy. That'd probably be easier. Make a copy. No, this is it. Make a copy. Okay, and then I'm going to run it just to make sure it's working. And then, so that was my other differential equation. And now let's just do it again. So I'm going to make two curves, okay? And then it's still running. I don't like to interrupt it when it's running, right? Because like, hey, it's doing its thing. So let's just make another curve. F2 equals G curve. Color equals color dot red. And dot equals true. So I'm going to calculate it two different ways. So let's just reset all my variables over here. Yeah. So t equals 0. Theta equals 45 times pi divided by 180. And theta dot, which, yeah, I do need theta dot. I don't use theta dot. I use p. So let's just put it as p. P equals 0. Note, I'm going to put a note here. P equals m r squared. Oh, r, that's right. R squared times theta dot. And I don't need to start off with the theta dot because I'm starting off with P. Now I'm just going to copy this. No, let's just do it again. So I'm going to say while t, let's change these to 3 seconds because I can't wait 5 seconds. It's too long. While t is less than 5, rate 100. And the first thing I'm going to do is to calculate, I'm going to calculate P dot. So I'm going to say P dot is equal to negative m times g. So I do keep that m in there. You notice that? I have it up there. Okay. Neg times r times cosine theta. That's what I wrote in my paper. P dot is negative mgr, no, sine theta. Now I'm going to use that P dot to update P. So P equals P plus P dot times dt. Now I updated P, I can calculate theta dot. So I'm going to look at my equation for theta dot over here. Theta dot is equal to P divided by m times r squared. Now I can update theta. Theta equals theta plus theta dot times dt, and then I can update time, t plus dt, and then I can plot it. F2 dot plot t theta. Yeah, I want it to match the other graph, and then we'll change it. I think that's right. I think. Just double checking. Yeah. Okay. Let's see if it's the same thing. So it's going to run the first way. This is Newtonian / Lagrangian mechanics with the theta double dot for 3 whole seconds. And now we're going to go back right on top. Same thing. So instead of having one second order differential equation, we have two first order differential equations, and I ran it for 5 seconds, I guess. Or did I not update time? I said 5. Why did I do that? Okay. So there you go. That's Hamiltonian. Now, we actually, since we're talking about changing theta and changing theta dot, one of the things we like to do is to make a plot of momentum versus theta. And we call this a phase space. Some call it phase plot, phase diagram. I've seen it different things. I don't really care what you call it. Phase space plot. So let's do that. I'm going to copy this. Let's just copy the whole thing. Save this. No, I don't need to save it. Okay. So let's call this, change this to X title is theta, Y title is P. And then I'm going to put, it's equal, right? So I'm going to say 500 by 500 just to make it fun. And then we're just going to do F1. So I have G theta. I need P equals 0. I don't need that theta dot. And then I'm going to get rid of this. I don't really care about that. I'm going to do this loop. Let's do it for 5. And really all I'm going to do is to plot theta versus P. That's it. And let's see what happens. A little bit. Okay, there you go. So there's your phase space plot for a pendulum, and it's moving around in this orbital path. But we don't have to worry about ever extending, changing graph with respect to time. We can plot the motion here, and this curve, since we're assuming energy is constant, this is a curve of constant energy. Let me just show you really quickly what would happen if you switch the order. What if, let's say I do find P dot, find theta dot, and then update. So you switch these orders and it doesn't work as well. I just want to show you how we can tell it doesn't work as well. So down here, all I'm going to do is to calculate, I calculate theta. Let's then calculate theta dot. Okay, so I'm going to cut that and put it right here. So I'm just changing the order. That's all I did. That's all I did. Change the order. And let's run it, and it looks the same. But it's not the same. You'll notice that it doesn't get back to the same path, which implies that it has a changing energy. And so we have a bad situation here. It's exploding. We can actually fix this with the right order, or you could fix this by making a smaller time step, right? And then I need to increase this too, or we'll be here forever. So that's a much smaller time step, and that error doesn't make as much difference. And there you see it's back to the way it was. But it's a huge difference. It's really a huge difference to change it to this and change this order. Let's put it back the way it should be. Cut that. So if I update the momentum and then use that momentum to update theta dot, it works way better. Oh, and I didn't change the rate. Okay, so there you go. Now, why? Why use the Hamiltonian other than we have two equations? Because I can make this plot. I can make theta dot versus theta in Lagrangian mechanics too. So it turns out that we use the Hamiltonian because in other situations in quantum mechanics, the Hamiltonian becomes an operator. The momentum becomes an operator. So it's much easier to deal with these first order differential equations as operators in quantum mechanics and other situations. But there you go. Pendulum, 3 different ways, and under 40-minute video. I'm looking at the clock right there. If you made it to the end of this, give yourself a high five, because that's a lot. Okay, I'll talk to you later.